Swayam Prabha. Digital India. Educated India.
Welcome to the subject Advanced Digital Image Processing and Computer Vision. We are discussing about video processing, and in the last lecture we discussed how videos are represented using compression. Today we will consider two particular issues of video processing. One is that what is meant by a shot in a video. This is a particular typical characteristics of video processing for detecting shots in a video, and the other one is that how the feature descriptors could be extracted from a video. So a shot, as you can see, that it's a set of consecutive frames of a video. So it is just not a set of consecutive frames. That's I should say that's one of the properties of being a shot, but essentially a shot of a video means that the scene has been captured by a constant camera parameter, by a fixed camera parameters. That means there is a specific view and specific camera on which the video has been captured. So it is depicting some kind of event or some kind of phenomena in the scene, and it is related to that. Now, when we consider a shot in a particular video, let us understand why do you require it. Because when videos are captured, there are various ways these videos are captured under various contexts. For example, you consider a sports video which is being broadcast. Now, in that case, there are cameras, multiple cameras for taking the videos of a sport. But when we are transmitting the program as a broadcast video, in that program, those several segments of at several time instances, there is a transition from one camera to the another camera. Not only that, when a particular scene is being captured by a single camera, there also the camera parameters, they may change. One can rotate the camera, one can sweep the camera for taking the panoramic view of a particular scene in a video, or one can perform the zoom in or zoom out operation on the same camera. But finally, what is being recorded as a video, it is basically in a linear progression of time. It captures all the frames of sequences with that kind of intervention by the human operator. So when we consider a shot of a video, a shot is a particular specific set of frames with the with that specific camera parameters. If we, in terms of vision, we have already seen that when we consider a single view camera, particular camera, then the camera geometry defines the projections of the world coordinates into the image coordinate. That defines the projections, and when you are capturing at several time instances as a sequence of those images, that becomes a video. So that is what some of these characteristics are depicted here. It could be considered as a maximal continuous partition of a sequence in temporal domain. So here also you may notice that we consider certain kind of continuity. That means when we consider a video, we have already discussed video can be considered as a function of space and time. Each image we know that there is a spatial, it's a spatial function, that is what is an image. But over time, when you have the sequence of images, then time becomes also another variable. So any pixel at a particular frame can be expressed as a function of space and time, any the brightness. So that is the brightness value or color value that varies over space and time. Now, when we consider a shot, now this function is, we consider this function is continuous over that time interval, which means since there is no change of imaging parameters, so we can consider the function also is continuous. So that is the kind of I should say real time, or that is the kind of real life constraints on a particular shot. But when there is a transition from one shot to another shot, then this continuity breaks down. So that is why we consider it's a maximum continuous partition of video sequence. Then without interruptions, as I mentioned, that from the operator's point of view, it's operator's particular specific handling, specific setting of the parameters on which video is being captured, and it's a single capture device for a shot. There could be multiple cameras, but when we are considering a shot, all the sequence of frames have been captured by a single device at its single parameters. Then there is also another concept which is akin to a shot but little different. We call it GOP, or group of pictures. Now, a group of pictures in a video, it's a fixed length syntactic segment. That is how we define it, which means that by definition we are considering a group of pictures is a set of frames or a sequence of frames of certain length, which has been already mentioned, pre-decided, and it's fixed. So over the videos we make partitioning with that length. So GOPs are all non-overlapping, but they are of same length, means they have the same number of frames in their sequence. That is what is for a GOP. A shot could be also a part of GOP. Like a GOP may contain the frames of a single shot, or it may contain frames of different shots. But a shot is in a shot may not may not be the same as GOP, as you can understand. It is variable length. It has, as I mentioned, that it is a maximal continuous depiction of that video from a single position of a camera. So that is what is a shot, and it has certain semantics. A shot has the semantics that it is depicting a particular phenomena, particular event. They are all related. When we consider a GOP, there could be frames of multiple shots, adjacent shots, so they may depict two different phenomena. So these are certain things that we need to consider. So now let us discuss that how shots could be detected. So this is one of the tasks of video processing, and I should say this is one of the pre-processing tasks, because once you detect the shots, since they are depicting a single phenomena, they are very much related to a particular scene. So after that, you consider describing the shots in terms of feature descriptors. So a video can be considered as a sequence of shots also. So the objective of shot detections, it has been mentioned that we need to get the information about specific objects are seen. That is the information we require, specific objects or events. And there are various uses or applications of the shot detections, and followed by the analysis of the video for video abstraction or summarizations, annotation, indexing, or semantic analysis, that means interpreting what is there in the video. Content-based retrieval, that means you have a library of videos, and given a query video, you would like to find out the similar videos. It's something like the search what we do using different search engine. So given a query word, we would like to get the documents. Then given a query image, we like to get the images. Similarly, given a small clips of video, we'd like to get the videos of similar things. And of course, the classifications. So for videos also, we would like to classify several events, say human actions, videos of human actions, and we would like to want to know that which actions are there in that video, whether a person is shaking hands, whether a person is cooking something or boiling water or lifting some weight. So different kinds of actions for the video could be of different kinds of human actions, and the task could be that given a video of certain action, you have to identify which action it is. So this is one example, but there could be various other kinds of classification problems involving the video processing. We should understand that the shots are created not only due to transitions from one camera, switching over from views from one camera to another camera. There are something also there when we produce a video. There is a human editor who is editing a video and make these transitions different types. Like transition could be very hard transitions. That means we call it hard cut. It is simply that the consecutive pair at the transition, one frame belongs to one of the shot, the other frame belongs to the other shot. So this is called hard cut. But when there is a gradual transition, that means there is a mixing of frames of two shots in between in the transiting sequence, that small time interval where the transition takes place. In those sequences, there is certain kind of mixing takes place, so that the frames of one shot fades out and the frames of other shot fades in. So it appears. So these are the soft cut transitions, and there are different kinds of transitions in the language, the technical terms of video editing, like fading, dissolving, wiping. So each one of these also could be considered as a task to identify. Given a video, you would like to detect the boundaries, short boundaries in terms of these transitions, and also types of transitions. So these are certain examples of short transitions. As you can see that this is the example of hard cut, where you have the frames of one shot and the frames of other shots, and by the color we are showing simply that one frame is followed by the frame of the other shot. So a very distinct transition from one shot to another shot through this color change we are seeing. Whereas the corresponding gradual transitions here, the gradual transitions, you call it dissolve, transition dissolve. So there is a mixing. So one frames of one shot is slowly or gradually disappearing, and the frames of other shots is appearing. So you can see that there is an additive mixing in these transitions. These are gradual transitions. Whereas fade out and fade in, as you can see that the frames of the shot itself is gradually, those intensities are diminishing, as if those intensities are diminishing, and other shot the intensities are increasing, and in between also there could be additive mixing. So this is that fade out, fade in, transitions. That's what we can understand. So our objective would be to, given a video, you have to find out those frames where these transitions are taking place, and also identify the types of transitions. So there are two particular approaches for short boundary detection. For doing that thing, first, it is basically frame-based approach. That means you consider every frame, and then you check whether this could be a frame of transitions, something like that. So what we do for that, we represent the frame by their feature vectors. Again, some description of the frame should be there. So there could be different types of descriptions, like intensity, color, age, or object through which you can describe a frame. Then there is certain measure by which you characterize this information of a frame. You distinguish this frame by that information. So And then this is a measure is giving some kind of numerical representations. It could be a vector, it could be a scalar value. And then what you do, you expect that for the same shot, these changes of this measure is slow, it's smooth. But when there is an abrupt change, then you consider there is a transition. So what you do, that you define a distance between these two measure or feature vector, and this distance is itself, when you particularly consider the distance as a measure of transitions between consecutive frames, and if it is greater than certain threshold, then we say that okay, the shot there is this frame is a transition frame, and these two pairs of shot where this threshold is quite high and quite significant. So you see that these pairs of consecutive pairs, they define a short transitions. Now, depending upon, of course, threshold value, you can consider a set of consecutive pairs, consecutives of consecutive pairs, sequence of consecutive pairs itself will give you a short boundary for soft cut. So this is a kind of approach which is a threshold based approach, because you are considering a threshold, and one of the issues would be that how to determine this threshold. Now, empirically one may observe and one may choose this threshold. It could be a fixed threshold, or one may consider certain kind of adaptive threshold, which means suppose I take a few frames around, say this is the frame of my consideration. So we take frames ahead of it and frames after it, and then we observe that how this measure. So take the statistical distribution of this measure, say if it is a scalar value, and find out that what is the mean and average. From there, you can find out what could be the threshold value which is not expected from this distribution, which could be outlier of this distribution. So with certain, this could be a method. I just mentioned one such method using this kind of statistical distributions, and that's why this sliding window. So this window could slide over the frame, and every time you make this kind of statistical test and find out whether the measure is significantly higher compared to the measure of the other. So we have to determine certain threshold in this case. So that is adaptiveness, what is mentioned here. So this is a threshold based approach. On the other hand, the other approach is the classification based approach. In this case, what you do, you classify a frame as, there are three classes we consider here: normal frame, hard cut, and or soft cut. So these are the three types of classes. Again, as you understand that this classification could be, this problem could be formulated or could be designed in such a way that first you describe the frame using the features. We will see that some of the feature descriptors later on for a particular frame, and those could be a vector of the classifier, could be the input vector of the classifier, and classifier needs to be trained using annotated data. So for that, what you require the training data set. That means annotated data set, training and test data set to design a classifier, as you understand. So the same kind of classification approach. There are three classes. There are training data sets. It says that which frame is what type it is, whether it is normal, whether it is a cut frame, hard cut or soft cut frame. And then once each of them is represented by a feature vector, and then you design a classifier which will try to classify based on this training data. So once you derive this model, now you apply in general situation. So this could be one such method, one such approach for short boundary detection. This is just a summary of the various approaches of short boundary detection. And as I mentioned earlier also, videos could be available in the form of uncompressed video, or even in reality, when you are storing a video, it should be compressed, or when you are transmitting. But there could be some real-time scenario when you are just capturing in the videos in the camera, and immediately you are processing them. So for that, that is an uncompressed stream on which video, on which in a buffer you can store those frames and you can process them to identify the short boundaries. Apart from that, even if you have the video in the compressed form, you can always apply the decompression and you can work with the uncompressed frames. So when we are considering uncompressed video representation, which means we will be working on the spatio-temporal domain of the video representations. And there, for each frame, since it is frame-based representation, so the temporal information is not really, that dynamics are not modeled in this representation. Each frame, like an image, the way image descriptors are there, similarly from there you can have local features which could be of pixel based, so local features which could be of pixel based or edge based features. It could be or global features which could be of histogram based, or intermediate feature which could be of block based features. So size of that. So blocks are again used for represented by the features, and set of blocks or catalog of those features will represent the total frame. And apart from that, video has its own characteristics, like you can consider its motion and also the representation of objects in that video, and the way the objects are changing. That could be also a considerations for detecting the short boundaries. Whereas in the compressed domain, we discussed earlier also that directly in the compressed domain representation, particularly the corresponding transform coefficients, you can, using transform coefficients, you can design algorithm, work with them, and you can detect the shorts. It could be density based representation as a popular transformation. Even the motion vectors we have discussed earlier, motion vectors are also there in the compressed stream. It has been computed when we are compressing a video. So why don't we use those motion vectors and for the short boundary detections? Or you can consider a mix of both. That means both the density coefficients and motion vectors, and using them you can design an algorithms. About the approaches, traditional approaches, machine learning based approaches are used in many cases. There are SVM based approach, or there could be random forest based approach, or the decision tree, basically set of decision trees. That is what is random forest based approach. Or even you can consider deep learning based approach, where the CNNs are used for classifying frames on different types of shorts. Now, regarding the feature vector representations and also the kind of dissimilarity functions which is used for in the threshold based approaches, let me throw some more light on it. Now, the distance function what you use is a standard distance function that you can see here. It's basically LP norm. So it's called mean Minkowski distance. Again, it is LP norm, and you are making distance between consecutive frames. And Zik is the respective feature vector which is representing a particular frame. We are expecting that consecutive frames, they should have small changes, and that is captured by this distance. But if this change is higher than a particular threshold, we consider that's a short boundary. And this LP norm, usually that P equal to 1 and P equal to 2, which means in this case L1 norm or city block distance, or L2 norm or city Euclidean distance. These are two popular choices. In the pixel based approach, for the local features, we simply use the pixel values, difference of the pixel values in the corresponding frames, and then sum of those pixel differences. So it's basically, I should say, the magnitude of the difference picture. So you take the difference picture, that means in consecutive frames, and then you take the sum of all those magnitudes of differences. Now, if it is greater than a certain threshold, then we consider that it's a short boundary. Whereas in the edge based approaches, instead of taking this kind of measure, we only consider number of H pixels between consecutive frames. We are expecting that this edges, they are actually are describing some objects within the video. So since the objects are not changing that much in a particular shot, so we consider the number of H pixels in a frames that would remain more or less in the similar range, more or less. There should be minor changes, or there should be small changes in consecutive frames. Whereas in a transition, this change would be quite significant. So, so this is the advantage. Though other special informations are not used in edge based, but still it is found to be a very good effective measure for detecting short boundaries, particularly using this kind of threshold based method. So that was for the local feature representation. For global feature representations, again you can consider histograms of frames, and then the difference between two histograms using say L1 norm itself. That could be also a good measure for threshold based approach. And as you understand it, since histogram gives you overall distribution of the intensity values, it is less sensitive to object and camera motion. So this is somewhat, I should say, limitations of this scheme, because the shots, when the short transitions takes place, it is expected that the object shape is one of the crucial key information. Similarly, camera motion is one of the key information by which shots are created. I should say there are key reasons driving this kind of short changes or causing there are major factors of causing short changes. This object and camera motion, they are major factors of short changes. So if I make the methods less sensitive to those two factors, it has certain limitations. In intermediate based descriptors, what we discussed earlier, like if I consider blocks, then use their statistical measures like mean, variance, histogram or likelihood ratios. Those things you can use for short boundary detection. And the classification based approaches, one of the example could be support vector machine based short boundary detection. So this is from a paper, as you can see that this is the paper what has been mentioned here, simultaneous detection of abrupt cuts and dissolves in videos using support vector machines, and the name of the authors is also mentioned. So it's a typical example. So what it does, it has a two-pass hierarchical process. Like first pass does the detection of bound cut detection, and the second pass for gradual transition with fine self. So that's the hierarchy, because hard cut and even the soft cut. So cut detection is easier to detect, but the type of transition, that means whether it is dissolve, whether it is wipe, whether it is fade in or fade out. So that requires more, I should say, distinctions. Those are a bit more difficult. So once we identify the cuts, then around that cut, it becomes our regions of interest or intervals of our interest. There we apply more detailed techniques to find out this type of gradual transitions. So one of the typical representation of feature vector could be color histogram. So we have a few moment measures, and here the three classes what we considered normal sequences, hard cut and soft cut. And in some cases what happens that we may use only first few sequences or first few frames, first few, I should say, time, few minutes of video, where in a minutes of video you get quite a bit of frame, and also we should see that there are different kinds of transitions, because what we do, we annotate that set of frames and use it for training, and then after that, that model being used for finding out the respective all the frames later on. But since it is active, it needs to be also updated. That means when you find out a new cut or new development transitions, so use that information, use that knowledge to update your model once again. So there is some techniques for that which could be used for this kind of boundary detection. So that was about the short boundary detections. Now let us consider the other aspect of video processing, and which is extracting the feature descriptors or representing a video by its feature descriptors. So in a video we have these spatio-temporal features, because video is a spatio-temporal function, and there are two particular types of approaches. One is that we consider the video as a three-dimensional volume. That means we have the two-dimensional frames, and then over time it makes a volume. So video can be considered as a three-dimensional data, like the data we use for three-dimensional images in medical images. And then the way these three-dimensional images are used for extracting, for representing their features, you can apply those filters on those volumes to represent videos with different kinds of features. So these are certain things, and I mean, this is one approach. And one of the things you should note down, that because of filtering, it may smooth out the motion region, particularly Gaussian filtering, it may smooth out that motion region. So one of the other approach would be similar to the spatial domain approach, that why don't you find out the key points in a video which are invariant to different kinds of transformations on that particular scene. That means there could be change of illumination, etc. And still, those points are expected to be detected. So these points are known as spatio-temporal interest points. So we will just elaborate that the way one can detect these spatio-temporal interest points. So one particular computation, one particular algorithm is something similar to the Harris corner detection in the three-dimensional volume. So what we do here, first we perform a smoothing of the image, smoothing of that volume using a Gaussian filter. Now this Gaussian filter, Gaussian kernel, is an anisotropic kernel, or it's a three-dimensional kernel. As we see, there could be three standard deviations, but what we consider, there is two standard variations or variances or parameters related to standard deviations. One due to space, variation in the space, and the other due to other over time. So this is a distribution over space and distribution over time, the Gaussian distribution, and that is why it is called anisotropic, because these two are not the same. So it is it has independent spatial variance of sigma square. So these two are not same, and these two are independent from each other. Then what we consider, that we perform the second derivative operations, that means we compute Hessians on that three-dimensional volume. So, but while doing it, we also smoothen smooth it using a Gaussian filter. So similar to what we do for Harris corner detections, there of course we have considered the first derivatives, and basically we have considered the square of the first derivative of a particular ix square, ix into iy. So That is the kind of matrix we have computed there. But here we have computed the second order derivative of L, and L is this one, which is the smoothened image. And then further we are smoothing this particular derivatives. So it is the same, either you smoothen out the second order derivative function itself, take the Gaussian of that, derive it take the second derivative of Gaussian kernel and smooth and perform convolution, or you convolve a second order derivatives of the function and then convolve with Gaussian. So it means that what you are doing for that particular volume, three-dimensional volume, we are getting the computing the second order derivatives at each point for derivatives along x direction, along xy direction, xt direction. So there are 9 such different kinds of measurements that you can perform at a single location, and then the function of that, each one will give me 9 three-dimensional volumes, and then each one of them you perform smoothing, and that is what that gives you a set of 9 such 3D volume which computed the second order derivatives. Now at a particular point, what you are doing then, what is the value is there, you consider this is the Hessian matrix. So here again the same analysis, that curvature analysis which is applied, because for your interest point you would like to see that the changes in a direction is there should be quite significant changes by moving the functional value in any directions, which means the curvatures in any direction should be high, and that measurements can be performed using this eigenvalue analysis. Overall, since the smallest eigenvalue should be significant of this Hessian matrix, so this can be indicated by a simple measure of determinant of this matrix, Hessian matrix, and compute the trace, and you consider these values. So wherever it is, so in the same cases, as you see that wherever this is greater than a certain threshold or maximum, so the local maximum will give you the respective point of interest. And in the way you have performed for highest corner detection also, you perform non-maximum suppression, so that near about local maximum should be suppressed, and only whose peak is significant, that should be retained. So that is non-maximum suppression by which these interest points are computed, and there are certain other constraints by which this is computed. You note again the k value, which is 1 by 27, which is less than 1 by 27, that is suggested. So that was about the use of Harris, similar to Harris three-dimensional, Harris corner in 3D. There is another kind of method by which you can find out the spatio-temporal interest points, and we call them a spatio-temporal blob, by using the three-dimensional form of Laplacian of Gaussian. So as you know that in 2 dimension, if I have a function f, then its Laplacian would be, say, delta 2f delta x2 plus delta 2f delta y2. That means this is delta 2f. Similarly, in 3 dimension, since this is a function of xyt, the Laplacian would be delta 2g delta x2 plus delta 2g delta y2. So all partial derivatives, second order partial derivatives with respect to every independent dimension, and then you are taking the sum of them. That is, it's a scalar value, Laplacian value, as you can see at a point it's a scalar value. And this filter, this means that you need to filter the image using a kernel which is given by this function. So which is basically the second derivative of the Gaussian kernel in 3 dimension and multiplied by the sigma q value of the space. So this is what is the Laplacian. Actually, it should be here sigma square tau, because you have two variables here. This should be also sigma square tau. So this is the function which is convolved, you perform the convolutions of this function with the image, and then it is something like again difference of Gaussian operations for applying the detection of key points in shift descriptor. Here also what you consider that find out that so in this case also what you do, you find out the extreme values of the second order derivative, and those extremal points, they are your key points. And as I mentioned that Laplacian of Gaussian operations can be also approximated by difference of Gaussian operations. So we can use also by 3D difference of Gaussian operations, which are easier to compute in a particular case when we are doing this representation, that scale space representation of a particular image. So just to summarize that what are the different types of techniques, some of them I described here, and some of them are mentioned here. It is easier to understand. So the spatio-temporal interest points, there are spatio-temporal corners, and the method out of which we have discussed Harris 3D method. There is also another method called cuboid method, by which you can perform this, you can compute the spatio-temporal corner. Whereas for spatio-temporal blob detection, you have Laplacian of Gaussian distributions, Laplacian of Gaussian operation, where extremal points are used to detect the spatio-temporal interest points, or you can use the 3-dimensional shift descriptors and also detectors. So as you see that once you get a key point and then you get its orientation and scale, then like shift detection, you can again accumulate the local orientation, statistics of local orientations by performing the rotational, taking care of rotational invariance. So this is what would be 3-dimensional shift as an extension of 2-dimensional shift, what we discussed earlier. And there are different other variants of shift like SARP, etc. that could be also used for describing a video using this kind of video descriptor. So here we come to the end of this lecture, and let us summarize that what are the things we discussed in this particular topic. First thing is that a video is a sequence of frames, as you can see, and we should have compressed representations, which means it should have motion compensation. We discussed about compressed representations involving motion compensation, residual error encoding, motion vectors, and intra-frame prediction. So these are the 3 major features of the base compression schemes. And then we discussed about short boundary detection, where dissimilarity among consecutive frames can give you a short boundaries, just identifying that dissimilarity. And the classification approach could be applied, classification methods could be applied, where we classify the frames by their transition types. And then we discussed about some of the methods of detecting spatio-temporal interest points, like there are Harris 3-dimensional 3D detector, corner detector, and for spatio-temporal blobs we have Laplacian of Gaussian in 3D or difference of Gaussian in 3D. So these are few things. So with this, let me end this particular lecture, and thank you very much for your patience and listening.